All right, everybody, welcome to Earth Science. So sorry, got interrupted there by the announcements again, so I decided just to go home and do the rest this morning. So good morning. So where I left off, I was mentioning that these are very stable, predictable, repeatedly, um, these numbers work out. It doesn't matter if they get hot or cold or under pressure or not under pressure. It just works as a matter of basic chemistry and statistics. So they're very accurate long-term clocks. This one that's 5,700 years, like you want to aim for half-lives if you're going to really do this that are around maybe 2 to 5-ish, 6-ish half-lives deep. After that, the curve really gets so low. You know, if you're in this range, you can tell pretty easily. But if we were to keep on doing this with the die, it would like get really flat here. I don't know if you've done this in math, but it approaches the value 0. And once it gets so low, it's really difficult to determine between one half life and the next, right? So carbon 14, by the time you get past, um, maybe 50,000 years, say that'd be even longer than necessary. But once you get that deep, carbon 14 is going to be so low that it's not really worth it. So we need much slower decaying isotopes to get to the deeper parts of Earth's history, to really get way back in Earth's history and figure out how all this has gone. Which is kind of the reason, and I don't know if this analogy is going to click with you, but it's the reason why I do a 6-sided die experiment and then normally do a 20-sided die experiment, to show that that 20-sided die one took a lot longer. And I know we didn't really do it this year, and again, maybe we'll get some people to play with it today. But that's this important idea. Some isotopes take longer to decay. How could having different isotopes which decay at different rates be helpful? So, like, for example, carbon 14 is good, say, up to, I think, maybe, let's say 40,000. And then the other three, we won't type them all out here because it'll take forever, but potassium, uranium, and rubidium, the other three on the ESRT, are good for much older timescales. That's how we figured out how old the planet is by working with some of that. Okay. All right. So now it's graph time. Let's do it. I'm going to zoom down a little bit here. What I'll do, those are my only two options. There we go. That wasn't bad. We're going to do time over here. So as time runs forward, and I did this experiment in minutes, right? And then the percent of the isotope remaining over here. And what I'll do is I'll get it started, then I'll pause, and then I'll complete it so that you can see it. So we said that this took 15 minutes. I said that me shaking the dice cup, dumping them into that tower, separating out the ones, putting them in the decayed jar, putting them back in the thing and shaking it again, each took about a minute. So we're going to say those are minutes going forward. And I've got on my lab enough to say this. So we're going to make the origin. In fact, I just think blowing these up so you can see it is going to be the way to go. So we're going to say that the origin, which I want in a darker color, right here, is 0 minutes. And then I think I've got this. I'm going to pause again and do it so that every 4 boxes can be a minute. So 1, 2, 3, 4 is a minute, and so on. Let me pause, do the whole axis, and then we'll see if it worked and come back. Okay, looks like it worked well. So every 4 boxes is 1. You'll probably want to press pause and do that. This axis is in time, in minutes. All right, and we needed 15 and we got right to there. So that looks good. The other one, there's a bizarre number of boxes. I don't know where I got these graphs. But over here is going to be percentage of dice and ideally you want to use a lot of it, but I think I counted 37 boxes, so that's feeling kind of weird. So I'm just going to go with every box being 5. We won't use the whole graph, but hey. I won't be mad at you. Every box is 5. I'm labeling every other box just to make my life a little simpler and neater. Again, that's what it's looking like. Let me pause and do it so you don't have to watch the whole painful thing. And we'll be back. Okay, we're back. So that's what it should look like right there. And again, if you've got to press pause to do that, not a bad idea. That'll get us right up to 100. Don't have to go. So we're not going to use, oh, look at all the graph we're not using. Painful. That's painful to me. But what are you going to do? All right. So that's what we should look at when we're zoomed out a little bit. Now we're going to need the data. So I guess I'm going to have to get you this. You can pause the YouTube screen, but maybe I'll come up with a way. I'll put it on the survival guide. How about that? So we're going to plot this column and this column. Let's do a little rounding here. We'll let Excel do the work. Okay. And this is really what the graph's going to look like. So sneak preview. So at 0 minutes, 100%. Use a color you'd like. If you make a little bit of a bigger font, then all you got to do is click for a dot. So at 0, it's 100%. Dot. Job done. Next. At a minute, 81.3. At 1 minute, 81.3. Looking like right about there. Click. And so on. Get the hang of it? Want one more? At 2 minutes, 67.1. Click. I think you can do it. All right. So take that all the way to 15 using the data that hopefully I remember to put into the survival guide. All right. I'm gonna do that because I'd like to talk about it. So you should do that. We'll press pause, and we'll be good. Okay, so this is what we should have. And again, the whole point of half-lives is predicting how long it's going to take to get to 50%. So doing that graphically, it might have even been, we probably should have done the above part with the graph, but it's okay. And I probably should connect the dots. Let me connect the dots real quick. Okay, dots connected. So we get to 50%, then you can come over to the line and come down, and you could really get exactly. So maybe that was like 3.25 minutes. See, we were off by a little bit just by estimating. When do we get to 25%? Well, it should be another 3.25 minutes on top of that, which is right about 7, which is about right? So you get the same half-life repeating and repeating and repeating because we did enough trials, and that was only 7, where we really should do many, 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 right? But you do enough trials and you get a very repeatable, stable decay through this half-life process, through randomness, through each die on its own being rolled, eventually coming up with a 1. Okay. All right. Question time, which I'm going to do as a separate video. Some of these are going to be a little tricky. This first one's perfect, though, because it's going to take you right through how to really figure out all of them. Okay. So good job for now. Questions on the next video, and then you're done with labs and science. Congratulations.